In the next couple minutes, we're going to talk a lot about electrons. First, we're going to start out looking at an atom and looking at the spaces in an atom where electrons can live. Then we'll learn about the most important type of electrons in an atom. These are called the valence electrons. We'll learn how you can figure out how many valence electrons an atom has by looking at where that atom is on the periodic table. And finally, we'll look at how you can take an atom and draw one of these electron dot diagrams for it that shows how many electrons it has. So let's get started. Okay, so check out this diagram of an atom I have here. In the middle is the nucleus with protons and neutrons. And now look at all of these little circles. Each one of these circles represents a spot that could hold one electron. You can think of these as like parking spots for electrons, or like theater seats for electrons. And these spots for electrons are organized into these circles. These circles are called energy levels or shells. You can think of these energy levels or shells sort of like they show the path that the electrons would take as they're spinning around the nucleus here. But also, energy levels or shells arrange electrons into different groups that are varying distances from the center of the atom. Okay, so for this first group, this first energy level or shell can hold 2 electrons, really close to the nucleus. Moving out a little bit, we get to another shell that can hold 8 electrons, and they're spinning out here. And then even further out, we have another group that can hold 8 electrons. Now it keeps going from here, and there are more and more energy levels or shells. But it gets a little bit tricky, so I just wanted to focus on these first 3 to give you an idea of how they work. Now, if you've learned a little bit about atoms already, you might know that the way I've drawn this here, this isn't the most perfectly accurate way to represent electrons and atoms. But you know what? It doesn't matter. For our purposes right now, we just want to learn the basics. Drawing and thinking about atoms like this is totally fine. So don't worry that it's not super accurate. Okay, so let's look at what happens when we start filling these electron parking spaces, when we start filling them with actual electrons. So we're going to use the periodic table for this. We'll go column by column. And here's what I'm doing. I've made this big version of a periodic table, and you can see it looks a little bit different than the real version of a periodic table, okay? Look at this whole thing in the middle. This is sort of a big, real periodic table. We're not going to worry about any of these elements in here in the middle. So this whole section, I've put it here. Just gotten rid of it. We're not going to worry about it. We're only going to focus on 8 columns. We're going to focus on these 2 right here, which I've drawn there, skipping everything in the middle, and then we're going to focus on these 6 over here. So don't get confused by the way I've drawn this. We're just leaving out some of the elements that we don't want to get into right now. Okay, so let's take the first element right here, hydrogen. Now, how many electrons are there in hydrogen? Okay, well, what we got to do is we got to look it up on the periodic table, and we're going to find something like this. Now, the periodic table, it doesn't actually tell us how many electrons are in hydrogen. It's got this 1 here, but that refers to the number of protons. So there's 1 proton in hydrogen. That's what its atomic number is. Now, if we assume, though, that this hydrogen atom, if we assume that it doesn't have a charge, then the number of electrons is going to equal the number of protons. So hydrogen always has 1 proton, but if the atom is neutral, if it doesn't have a charge, it will also have 1 electron. So let's go back to this diagram of the atom here. Let's just start with this first energy level. Okay, here's a drawing just of the first energy level. Let's put a nucleus in here. I'm not actually going to draw the protons and neutrons. Instead, I'm just going to write the number of protons. Okay, so this has 1 proton, and P plus is the abbreviation for proton. So 1 P plus in the nucleus. Now here are the 2 spots in this first energy level where electrons can live. There is 1 electron in hydrogen, so we're going to fill that in. That was really easy, right? So we got this first energy level in hydrogen. 1 of the spots is still empty, and 1 of the spots is full. Okay, let's move down here to lithium. Now if we look up lithium on the periodic table, we're going to see this 3, which means that every lithium atom has 3 protons in it. But if that lithium atom is neutral, which we always assume that it is when we're doing this sort of thing, this lithium atom also has 3 electrons. So we'll start here. We'll be first concerned with this, this energy level that's right here, the first one here. I'm going to put a nucleus in here, 3 P plus, because there are 3 protons in here. Okay, so there are 3 electrons. So this one is going to get filled, and this one is going to get filled. And now we're going to want to go to the next energy level. Okay, now that starts getting filled. So now it's going to look like this. Now we want to start thinking about the second energy level. The first one is filled, and now 1 electron is going to go here in the second energy level. Okay? So these energy levels, they're really like parking spaces. Imagine that the nucleus is a mall, right? It's like the parking spaces closest to the entrance of the mall, those are the ones that fill up first. And then as more and more people park, the empty parking spaces move further and further and further away from the center of the mall. It's exactly the same way with atoms, okay? The first energy levels close to the nucleus, those are the ones that are going to fill up. And then, after they're full, the other energy levels further out, they're going to begin to fill up too, okay? Now, let's look at sodium. Sodium has 11 protons in its nucleus. 11 P plus, and we're going to assume that since it's neutral, we're assuming that it's neutral, it has the same number of electrons as protons. So let's start filling them in. 1, 2 in the first energy level. Now that's full, so we're going to start filling the second energy level. 3, 4, 5, 6, 7, 8, 9, 10. And finally, these are all full, but we still have more electrons, so now we're going to have to bump it to the third energy level. Here's a third energy level that we can start filling in. 10 of these are already living in the atom, so we're going to add 1 more. And now there's 1 in this third energy level. Okay, now check this out, because this is important. Hydrogen, lithium, and sodium, they all have different numbers of electrons. But there's a pattern here. Check this out. Each one of these atoms has 1 electron in the outermost shell. Okay, this one's full, but then there's just 1 here. This one's full, and then there's just 1 here. And then hydrogen here only has 1 energy level, and it just has 1 electron in it. These electrons, 1, 1, and 1, these are the valence electrons, the most important electrons in an atom. We'll talk more about that later, why they're so important. But all you have to know for right now is that the valence electrons are the electrons in the energy level that is the furthest out from the nucleus. So in this atom, the valence energy level is the third, and it has 1 electron. And here, the valence energy level, the furthest out, is the second. And here, the furthest out, the valence energy level, is the first. So there's a pattern. Each one of these atoms has 1 valence electron. That's true, not just for these first 3 atoms, but for every one of the atoms that's in this first column in the periodic table. I didn't want to do the electron structures for all of these others, but just trust me that they all have 1 electron. Okay. So now there's a way that we want to be able to write that, to show that these elements have 1 valence electron. And what we can do is draw what we call these electron dot diagrams. They're sometimes known as Lewis diagrams, where we take the element and then put 1 dot over it to show that it has 1 valence electron. Here's how we'd write the electron dot diagrams for all the elements that are in this column. As an example, I'll just take lithium and write it here. So every single atom in this column has 1 valence electron. Okay? Let's move on and take a look at some of the other columns on the periodic table. Okay, so if everything here has 1 valence electron, let's take a look at this column. Starting with beryllium. Beryllium has 4 protons. If it's electrically neutral, it's going to have 4 electrons as well. So let's look at how this fills in. We've got 4 protons here in the nucleus. And now we're going to go 1, 2 in the first energy level, and in the second energy level, 3, 4. Okay, so we've got 2 electrons in the outer energy level, and look at the way I filled them in. I didn't just fill them in clockwise here, but one went on the top and then one went on the bottom. Okay, now magnesium here has an atomic number of 12, so 12 protons and 12 electrons if we assume that it is electrically neutral. 12p plus here, so 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what's the pattern here? For this second column in the periodic table, we've got 2 valence electrons for magnesium in the third energy level, and we have 2 valence electrons for beryllium in the second energy level. So everything in this column has 2 valence electrons in this outermost shell. So what we can do is we can draw electron diagrams for everything in the second shell here, for everything in the second column here, and it looks like this. We take the element symbol and then we put a dot at the top and a dot at the bottom. And that's how we represent the electrons for here. So I'll just do like Be beryllium for example. I'll do Be, dot on the top, dot on the bottom. Let's go on. Okay, you're probably getting the hang of this, so we're going to start moving a little bit faster. Let's move on to boron here. Here's boron. This is the structure of boron. And then here is aluminum down here. 5 protons, 13 protons. And look at what the structure of the valence electrons is here. We've got 1, 2, 3 in the valence shell of boron. And for aluminum, we've got 1, 2, 3 in the valence shell. The same is true for these guys here, even though I haven't drawn them out. So if you're in this column, you have 3 valence electrons. An example of this would be boron. And look at how I do the dots for boron. Okay, I do a dot on the top, just like lithium. I do a dot on the bottom, just like beryllium. And then I do a dot here to the left to show that these all have 3 valence electrons. And it would be the same way for any of the elements in this column here. Okay, let's do all of these as a group. Okay, this column first has carbon and silicon. And each of these have 1, 2, 3, 4, 1, 2, 3, 4 valence electrons in their outer shell. Okay, so I can take this and do a dot up here, a dot down here, a dot to the left, and then a dot to the right to show that everything in this column has 4 valence electrons. Now moving on to the right, we've got this column with nitrogen and phosphorus and all these others, and everything here has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 valence electrons. So if nitrogen is my example, I'm going to do N, dot on the top, dot on the bottom, left, right, and now I start doubling up. So now there are going to be 2 dots on the top of nitrogen to show that there are these 5 valence electrons for everything that's in this column. You can probably see that there's a pattern that's developing here. Oxygen and sulfur each have, you can count them, 6 valence electrons. So I'll take oxygen as an example. Now look at what I do here for drawing the valence electrons because it gets a little bit tricky. You'll figure it out, but it's a little bit tricky. Okay, dot on the top. So anyway, 6 valence electrons for everything in this column. Oxygen is the example. Dot on the top, dot on the bottom, dot on the left, dot on the right. Now we double up the one on the top and then we double up the one on the right. Okay, so we don't put it on the bottom, we put it on the right. So up, down, left, right, and then around clockwise. Finally, for this column, which has at the top of it fluorine and chlorine, both of these have 7 valence electrons, which means that this valence shell is almost full, except for 1 hole in it. So I'll take fluorine as my example here. Dot on the top, dot on the bottom, dot on the left, dot on the right. Now we double up. Double up on the top, 2 up here, double up on the right, 2 there, and then double up on the bottom. So I've only got 1 guy here on the left that doesn't have a pair. Now here's the last column that we're going to talk about. Okay, look at what happens here. we'll look at helium, neon, and argon, okay? Here's helium, here's neon, and here is argon. Notice that argon has 8 valence electrons, doesn't have any empty holes in its valence shell. Neon also has 8 valence electrons, but helium only has 2 valence electrons. Okay? So what's going on in this column is that most of these have 8. Neon has 8, argon has 8, as do krypton, xenon, and radon. But then there's helium that only has 2. But regardless of whether you have 8 or whether you have 2, if you're in this column, your valence shell is totally full. Okay? So here it's full with 8, here it's full with 8, and here it's full with 2. But they're all full, and there aren't any empty holes in the shells. So as an example, I'm going to use neon, which has 8. So 1, 2, 3, 4, and now we go clockwise. 5, 6, 7, 8. 8 valence electrons for most of these guys, but remember that helium only has 2 valence electrons, but that all of them have valence shells that are totally full with no empty spots. So this kind of sums up everything that we talked about. Every atom in this column has 1 valence electron. Every atom in this column has 2 valence electrons. And then we skip over this middle section and we get 3, 4, 5, 6, 7, and 8. So if you know which of these columns a particular atom is in, you can figure out how many valence electrons it has.